Hello, fellow Physics 212 students. Welcome to our presentation for the first project for this quarter. I'm Herr-Williams, and myself, along with Tim McDonald and Adrian Fielding, will be presenting our solution to the turntable problem, starting with Tim McDonald, who will now describe the problem.
Okay, for my section of the project, I will be going over our description of the situation. We are given a problem where we have a turntable with radius of capital R that is rotating. On this turntable, we have a cube with given mass of capital M, and then we are given a hollow ball with mass of lowercase m and radius of lowercase r. There is also a string attaching the ball to the cube that is wrapped around a massless pulley in the middle of the turntable. Given all this information, we need to find the angular speed of the turntable. Now next, I wanted to go over the free body diagrams of both the cube and the hollow ball. So for the cube, from the center of mass, we have a normal force from the turntable onto the cube. Then we have a force due to gravity. And then we have a tension force by the string attached to the hollow ball, right? And it also has acceleration in the direction of the ball that is falling through the center of the turntable. Next, we have the hollow ball itself. So we have force due to gravity acting on the center of mass, and then we have a tension force acting from the side of the ball. So as the system starts, the ball will go to fall and it will unravel itself kind of because it'll have more rotational acceleration. As seen in the picture, I have an arrow indicating the acceleration of the ball as it falls. Now, off to Adrian, who's going to talk about how we solve the problem and all the math stuff.
Thank you, Tim, for setting this problem up for us and showing us some very helpful graphs. I will start to solve the problem with equations now. In the top left corner here, you can see we have the equation for net torque in terms of inertia and angular acceleration. Then over here we have the equation converting normal acceleration, or translational, to angular by dividing it by radians. Underneath that, we have net torque in terms of the cross product of the force vector and the radius vector. We have the parallel axis theorem telling us that we can measure inertia of a parallel axis off the center of mass. Then we have the force equation, which is mass times acceleration. We have the centripetal acceleration equation, which is velocity squared divided by radians. Then we have the angular velocity equation, which is just velocity divided by radians. And then, since we're using a hollow sphere in this case, our inertia equation is 2 over 3 mr squared, which we were able to find on the internet. To start it, we'll be using the torque in terms of inertia and angular acceleration and setting it equal to the tension force times the radius. You know, angular acceleration is just acceleration divided by r, so you can see we replace that there. And then solving for the tension force, we get inertia times acceleration divided by r squared. Now we will solve for the moment of inertia using the parallel axis theorem. We'll solve this by using the moment of inertia at the center of mass, then adding it to the mass times radius squared. With that, we get 5 over 3 mr squared as our moment of inertia. Now we'll be solving for the net force on the ball. That is given to us by the force, mass, times acceleration, and it's equal to mass times gravity minus the tension force, which we know as moment of inertia, times acceleration divided by radius squared. After doing some algebra and simplification, you can see we are able to cross out the masses, cancel them out, and we're left with acceleration equals gravity minus 5/3 acceleration. You factor out the acceleration and you get acceleration equals 3/8 of gravity. Now we know the acceleration of the ball. Now using that, we can solve for the force of tension of the string, which is equal to inertia times acceleration divided by r squared. And when we plug in our values here, we have the inertia that we had, and then the acceleration that we just solved for divided by radius squared. Then doing some algebra, we're able to cancel out the r squared, simplify the fraction, and we get 5/8 mass times gravity is equal to the tension force of the string. Now using the tension force, we can solve for the motion of the box on the disc. We know the tension force as 5/8 of the mass of the ball times gravity. Using that, we can simplify by multiplying the big R, radius of the disc, to the other side, dividing the other side by capital M, mass of the box. We're left with v squared equals 5 mass of the ball times gravity times radius of the disc divided by 8 mass of the box. Square root this side, and you're left with b equals square root of 5 mass gravity big R divided by 8 big M. Now we will convert the velocity to angular velocity by dividing the velocity by the radius of the disk. When you do that, the r goes into the denominator, and we're left with the angular velocity being square root of 5 times mass of the ball times gravity divided by 8 mass of the box, radius of the disk.
Thanks, Adrian. In order to make sure that our answer is correct, we have to first perform some sense-making strategies to make sure that our answer reflects the physical motion described in the problem statement. The first part of that process is, of course, to make sure that the units from our symbolic answer are lining up with what the quantity we want to solve for. So in this case, we want to solve for angular velocity. So our units, when we plug in units for each variable in the equation, we should end up with radians per second, or since radians are unitless, we should end up with just seconds in the denominator, or seconds to the power of -1. When we do plug in those units for our symbolic quantities, we do end up with seconds to the power of -1. So our units are correct for the quantity we want to solve for, angular velocity that being. Now that we know that our units are correct, we have to make sure that the equation gives answers that make physical sense when we plug in values for each variable. The best way to test the solution in this aspect is to use numbers that would produce an expected value for the angular velocity. So for our example, we decided to use a ratio of 1 to 10 of the mass of little m to big M, since this should produce a relatively small angular velocity. And that's because when little m is so much smaller than big M, we would expect that the net force on the system is also going to be lower, which will produce a lower acceleration for the system. And as a result, we would expect the angular velocity or rotational speed of the pulley to also be really small as a result. For r, we set that equal to 5 meters, and gravity was set to near surface gravity, since it can be assumed that this is happening on Earth. And then for our masses, we set big M equal to 50 kilograms, and then little m equal to 1/10 of that, or 5 kilograms. Plugging in those numbers, we get the rotational velocity of the pulley is 0.354 radians per second. And at that speed, it would take nearly 20 seconds for the pulley to complete one rotation. So this angular velocity does make sense given the values we plugged in, since it is a relatively long time for one rotation to occur. For the final part of sense making, we have to look for expected special or limiting cases for the system. For the physical situation described in the problem statement, it would make sense for the angular velocity to increase when the mass of big M decreases, since the force of little m will be acting on a smaller mass, and therefore the acceleration for the system should increase, such that the net force is still equal to the same value. Similarly, decreasing r should cause the angular acceleration of the system to increase, since it will decrease the net torque while the net force acting on the system is constant, and so it will be more likely to rotate, and the angular velocity of the pulley should increase. When r or m are equal to 0, the system cannot exist as it does in the original problem statement. So when r is equal to 0, there's somehow zero distance between large M and the pulley, which doesn't make physical sense. And with M is equal to 0, it creates a system where the string attached to big M and little m is not constantly interacting with the pulley, and therefore the system is unpredictable. We can't say whether the string will cause the pulley to rotate or not, since there's no force holding it together. This graph shows the angular velocity versus r when all other variables are held constant. Based on the graph, we can see that our expectation is constant with the system, or consistent with the system, since as r approaches 0, the angular velocity increases. It is also consistent with our prediction that the system will break when r is equal to 0, since the function is undefined at r equals 0, which makes sense based on the edge case we described previously. This graph shows the angular velocity versus the mass of big M when all the variables are held constant. Just like the graph before, this does show the expected behavior where as the mass of big M approaches 0, the angular velocity approaches infinity. In addition, it also does hold consistent with the prediction that when big M is equal to 0, the system breaks. Since at M equals big 0, the equation is undefined. And as a result of these sense-making strategies, it is clear that the model we have created is very accurate to the physical behavior of the system, as well as where the system does and does not exist, given the parameters defined in the problem statement. Now to Adrian for the reflection.
Thanks, Dane, for the sense-making. Now I'll be relating the turntable problem to other things that we have done in 212. Starting off, we have activity 2 from homework 3. This problem asks us to determine which axis has the greater moment of inertia, this one being in the center of mass, the blue one being in the center of mass, and the pink one being on the edge. We know that the pink one is just the center of mass inertia plus the mass of it, and then the distance squared. And since we know that you have to add to it, we know that the one on the edge would be greater. This problem introduces us to the parallel axis theorem, and we had to use it in our equations for solving for the turntable because the ball that was rotating underneath the table was not rotating about its center of mass, it was rotating about the edge because of the string. Knowing that, we found the moment of inertia for that spot and used it to solve for the rest of the equations. On the next slide, we have activity 3 from homework 3. It asks us to find the acceleration of all the objects in this system. In this problem, we use the net torque equations, inertia times angular acceleration, and the force vector times the radius. We can set them equal to each other because we know the moment of inertia and we know what angular acceleration is. Then using algebra, we're able to isolate the acceleration in terms of mass and gravity and acceleration. In the turntable problem, we use the two torque equations, setting them equally to each other, to find the force of tension in terms of inertia, acceleration, and radius. Since both problems were looking for acceleration, we used some similar methods, but it was different because in the turntable problem, the force is from the tension, and in the problem just looking for the acceleration of the boxes, the force of gravity was causing the acceleration.